possible.
But it's difficult.
You can try. Just try.
Does it look weird?
Yeah, and I suggest you turn the background into white, since people cannot see it clearly. Cool. It works.
Sorry, the feed to our stream got disconnected.
Oh.
I think the person who was up here before thought that it had gotten done. So I just wanted to. Yep, they disconnected it. At least they were taking questions.
Okay, so let's welcome James to give a talk on targeting accelerators with MLIR.
Hi. Okay, so the last question that someone asked was a great segue into my little talk, because the background to MLIR, which is a new compiler project out of Google, is that Google has a lot of accelerators and a lot of compilers, and they don't necessarily talk to each other or work together, or they weren't necessarily built by the same team. You have TensorFlow and XLA and TPUs, cloud TPUs and edge TPUs, and it's also, I mean, there are other accelerators in the world like GPUs and everything that's being built by this like fast-growing ecosystem of startups, and some folks at Google, led by Chris Latner, thought it might be a good idea to try to bring some sense to this this explosion of accelerators and compilers, and design basically a new compiler infrastructure, what Chris likes to call a compiler infrastructure for the end of Moore's law, because the end of Moore's law means more accelerators and heterogeneous hardware. And it's a compiler infrastructure like LLVM that you can use to build your own compilers. And if you build a compiler using MLIR, then it can work together with other compilers, and you don't have to rebuild all of the core infrastructure again and again and again. So basically, what is MLIR? It's like LLVM, but it has an open ecosystem of dialects, which are sort of categories of IR. And each of these dialects can bring its own set of operations, basically instructions, and its own set of types. And it can bring its own type inference for those types, and its own constant folding infrastructure, and everything like that. And then there's also basically an ecosystem of progressive lowering transformations that can convert between dialects, and that can so you can have multiple levels of IR in one program, and sort of progressively lower between them. I think that the key insight that that's based on is the idea that if you have an optimizing compiler, any transformation that doesn't change the semantics, so that just optimizes, is free to ignore any operations or any dialects that it doesn't know about. And so you can mix transformations and lowerings from different dialects, and sort of even from like that were written by different companies, things like that. So here's some just like brief examples of what MLIR looks like. It looks a lot like LLVM, has this textual representation. So you can, there's sort of some standard operations on these built-in tensor and memref types. Okay, so MLIR, maybe you'd expect that it stands for machine learning IR. It actually stands for multi-level IR. There's some other abbreviations, like it could stand for multi-dimensional loop IR, all sorts of things. But at least like the one major use case is in machine learning compilers for machine learning accelerators. So it has built-in tensor and buffer types. And you can just mix those kinds of built-in ops with ops that come from dialects like TensorFlow or XLA or things like that. And then it has like so it's a single IR representation that can represent both like bulk array style ops and also loops and loop nests and polyhedral loop nests and everything like that. So just like quickly some dialects that exist already. There are built-in and standard ops, which are sort of the core infrastructure that everyone might want to use. There's polyhedral abstractions for optimization of nested loops that follow certain constraints. There's a one-to-one embedding of LLVM IR, as well as SpearV for GPUs and mobile. There's a dialect of GPU kernel intrinsics. And then there are many dialects that live out of tree, out of the MLIR core tree. So things like TensorFlow graph ops, XLA, HLOs, and TF Lite. And there are starting to be a few dialects that weren't built by Google, including there's a proposal for a new mid-level IR for FLang, and some discussion on the mailing list from Intel about using MLIR for a machine learning compiler that they have. And of course, there's much more to come. So like, there's a lot of compilers and hardware at Google, and MLIR is hopefully going to help bring some sense to that, and some sort of additional open sourceness. So let's just like quickly look at what it might look like to use MLIR from Julia today, which is not particularly nice because I've just put this together over the last couple days just to maybe like see what it looks like right now. I'm using CXX, which is Kino's wonderful package for basically directly interacting with C++ code from Julia, including a lot of like pretty crazy runtime compilation tricks. You can get things like templating C++ code on Julia types and vice versa. And so once I've done that, I can create sort of just little mappings between Julia types and MLIR types and things like that. And then, okay, so the Julia type float32 has this representation, and this array type is this representation in MLIR. I can create a function type, and then create a function object, and then a builder for that function, and add some ops to that builder. And now I have a function that has some ops in it, including one from the XLA dialect. And then I can add it to a module. Okay, so that's like without building anything in particular in Julia, what it looks like to sort of build MLIR from Julia right now. There are some kinds of syntax sugar that exist for other languages in MLIR. So for instance, if you want to build MLIR functions from C++, there's this syntax, which they call declarative builders. And so that looks kind of like these nested scopes. If you use Python, there are these with blocks that you can use. These are sort of Python syntax sugar for building MLIR expressions and modules. And I guess I'm curious what that might look like in Julia. I think it would be a great fit. What would it look like to embed Julia ASTs in MLIR? What about lowered code or typed lowered code? I mean, why Julia? Because I think that one thing that MLIR is sort of crying out for is a like natively JIT compiled environment, because there's no built-in capacity for polymorphism, and that would bring those kinds of features. And I think like Julia plus MLIR could do some pretty cool things. So basically, I'm throwing down the gauntlet or laying out a challenge or trying to provoke the community or whatever. And just to wrap up, MLIR core is developed in open source at github.com/tensorflow/MLIR. And there's a very active development mailing list at mlir@tensorflow.org, including like core sort of direction proposals from inside the MLIR team at Google. So it's not just like sort of quiet external developer chit chat. It's like the sort of core decisions that like the core MLIR team is making are made in the open on the mailing list. So that's all I have. But I'm happy to take questions. Note that I do not work on the MLIR team, so I may not be able to answer everything.
Any question? Okay, so thanks, James. Great talk. Let's welcome the next speaker.